predicting whether a system's at equilibrium and determining equilibrium composition. I've changed a few things, but if you made hard copies of the outline, you're fine. I didn't change that much. So what's the big deal? Well, all of us are living, breathing organisms, right? So how do we do what we do? Where do we get the energy? Well, from breakfast, but what goes on inside every single cell? Glycolysis, right? And this is the overall reaction for glycolysis, but actually what's going on is a series of 10 equilibria all going on at the same time. But the point is talk about what's going on at equilibrium in any reaction, glycolysis or not. Doesn't really matter how complicated it is, right? It's the same thing we're going to talk about today. The power of this predicting equilibrium composition and determining whether something's at equilibrium or not in the first place is really pretty powerful. Let's do a little review first. Mallory, what does that little C stand for? Not constant, but you're supposed to use what units, Adrian, for concentration? We had several choices, if you remember exam 1, but we're always supposed to use what units for concentration? These Kc expressions. Give you a hint, it's moles over liters, big M, molarity, right? Well, moles over liters, that's right. Now we could, Lewis, go Google glycolysis and we can see what the equilibrium constant is. We can Google really any reaction and you get a number for these equilibrium constants. They're not really true constants. Because if you change one thing, this is the only thing you can change, and you can change those numbers. It's not a catalyst. It's not pressure. Is it? Well, you really can't change this. Oh, he's got a good point. You hear what Pablo was saying? If you change the stoichiometric coefficient, that would work. I never thought of that. I got to change my answer to 2 now. There's 2 ways, right? If you multiply this whole thing through by 2, this reaction, you're going to change that. In fact, you're going to square the Kc. So, oh, good. Yeah. All right. So that is, you could, but if you can't just mess with one stoichiometric coefficient, right? You have to multiply the whole thing through by the same number. But that would work. What was I after? There's the T. Temperature. So if you change temperature, equilibrium constants change. So it's gonna, don't let it confuse you because it's technically correct. If you give a reaction, you give the equilibrium constant, you really got to give it temperature too. Because if you don't, what temperature are you at? Because Kc changes temperature. So a little view, reaction, and Javier, there's the equilibrium concentration, and we just want a value for Kc. So what Kc expression could you write? What would be on top? Products over reactants. Right. Well, before we put in the numbers, let's get in a good habit of writing the actual expression. And I'll tell you why in a little bit. So on top, everybody, you're going to have what? Yeah, that C8. Now, where does the 2 go? Yeah, squared. Okay. And then on the bottom, everybody, you're going to have calcium squared, and the OH has to be cubed. Okay. Now, the reason why I strongly suggest this is otherwise we're going to be doing a lot of math. And if you forget to write one of those little exponents, you're going to want to shoot yourself at the end. So by writing this expression, I usually catch it. Okay, now we can plug in the numbers. Right. The concentration of calcium hydroxide is, there it is. But don't forget to do what to it? Square it. And then you got to have the calcium, and it's 4. But don't forget to square it. And hydroxide is 2.5. You got to cube it. Okay. So 2.5. Square it. Divide it by 4 squared. Divide that by 2.5. And you should have a cube button on your calculator, x cubed. I get 0.025. Okay. I changed some numbers on there. Okay. So that's what I get for my KC. Make sense? Okay. So one part of what you're going to see in the homework is, hey, is this reaction at equilibrium? They're going to list out all the concentrations, reactants, and products. About 0.025. Don't worry about it. Just if you know how to do it, that's what I'm after, to review. Okay. We'll play with your calculator at the end. I'll show you how to use it. Okay. How do you predict if something's at equilibrium or not? The answer is calculate QC. Matteo, what the heck is a QC? You're supposed to be able to calculate them somehow. How do you get it? Oh, it's reaction quotient. Yeah, but
it's still product of a reactant.
It's still product of a reactant. Exactly. It's the same thing as Kc, except just don't write Kc, write QC. Right? Cross this out and write QC. That's all it is. Calculate a QC. Okay, so we could have done that in that last problem. All of that would have changed is, hey, you're not at equilibrium. So you calculate a QC. And then you got to compare it to the actual equilibrium constant, Kc. And they're going to give that to you every time. Okay? So you go through the math and you get your QC. You find out, oh, it's too big. It's bigger than my Kc. Then I have too much, what? I'm not at equilibrium. Too much product. That's how I like to think of it too, because equilibrium constants are what over what? Products over reactants. So if my Q is too big, how do you get a number that's too big? Too much product. If I have too much product, then I'm going to shift back to reverse reactants. I'm going to go the opposite way. Okay. Another possibility, you calculate your QC ray by writing your Kc expression, substituting all the numbers. Now the number's too small. Now there's too much reactant. Too much reactant, so I got to shift forward, make more product. Okay. It's possible. You could go through all this work, Nick, calculate a QC. It's the exact same thing as Kc. It's at equilibrium. Right? It's at equilibrium. There is no shift. You're at equilibrium. You have the equilibrium composition right there in front of you. Okay. Now, we found Kc to be 0.025. Yeah, they got to give you the Kc. Like this question. They give us the Kc is given. Okay. However, these are the concentrations. Victoria, are we at equilibrium? How do you figure this out? Yeah, calculate a QC. Technical jargon, right, I guess. Calculate a QC. Product over reactant, right? So, calcium hydroxide. That has to be squared. The calcium has to be squared. The hydroxide has to be cubed. Right? And they said the calcium hydroxide was 13.4. Okay. Just don't forget to square it. And the calcium, they say that's 2.6. Just don't forget to square it. And the hydroxide is 8.9. Don't forget to cube it. So 13.4 squared, x squared button, divided by 2.6 squared. divided by 8 raised to the third power. I get 0.04. I could write even more digits, 0.038 or something. Okay. So Shelby, that's what I got, 0.038. Are we at equilibrium? No, they're not the same. Ooh, she got the next part. Did you hear? There's too much product. QC is too big. So there's too. So which direction is it going to shift? Yeah. Shift to reactant. Okay. Okay. Now that's a question you're going to be asked. This is the next type of react. This is the next type of question. And they're going to give us a KC, but what they want to know is what's the equilibrium composition. Helpful is if you visualize what is composition. What is the answer? You're going to draw a box around your final answer, Shelby. What are you drawing a box around? The equilibrium composition, but what is that? What is it? But not moles. We're going to use molarity, concentration. So you have to list every single reactant, every single product, right, and list their molarity. That's what equilibrium composition is. Equilibrium composition is going to be a lot of work, okay? So equilibrium composition, just burn that in your head. Oh, that's all the reactants and all the products, right, in brackets. You have to list their molarity. Okay. So the answer, Eddie, is to make a what table, then do what? Ooh, I heard that one part. Someone help you out. Do ice, but make a... You're right. Eddie, did you hear him? Make a concentration table. Because remember, you want equilibrium composition. So you want to give concentrations of everything. So let's not make a mole table, because then you got to go through and remember to divide everything by volume. So it's a lot easier to make a concentration table and get all your answers in one big step. And remember, Amanda, what units are we going to use for concentration? Big M, which is what over what? Moles over liters, right? We write big M because we're kind of lazy, but that's how we do it. Okay. We have a 1 liter vessel, 3 moles of chlorine, 5 moles of bromine are mixed. The equilibrium constant is 50. What are the final equilibrium concentrations? In other words, what's the equilibrium composition? So, Jessica Rojas, what should we do? Do ice. Okay. So, Pablo, what are you going to put in? Remember, what type of table do you want to make? Big M table. So, yeah, did you hear him? Got to divide the moles by the liters. How many moles of chlorine? 3. And there's just 1 liter, so it is just 3. But just wanted you to realize that, because almost all the homework, they're not going to say 1 liter, all right? So this is going to be 3. Bromine, everybody, is going to be 5. How about the bromine chloride? Dash, right? Healthier than zeros, because dashes work for solids and liquids too. Okay, the change row. Alexa, how are things going to change? Minus X? Yeah? Perfect. Excellent. Reactant change is negative. They're going down. Product positive. And she grabbed those stoichiometric coefficients. Good. The equilibrium rule, Mariella. At equilibrium, what are going to be the concentrations? 3 minus x, 5 minus x, and 2x. Okay. These are our answers. Those are the answers. Just have to find what x is. Okay. Jessica Vaughn, it seems like with our little there wasn't quite enough because we made a concentration table. We did, but you need to know what x is. So what are you going to have to do? What would be the next logical thing? Okay, she's using that 50, using the KC. Exactly. Right, the KC, you're right. What do you call it? The KC expression, right? The KC expression, right? And don't put in the numbers right away, right? The KC expression, otherwise you're going to forget to square something, right? Okay, so my KC, all right? KC is products all over reactants. And that's going to be BrCl to what power? Squared. It's going to be chlorine to what power? Yeah. And bromine also to the first. Now we can substitute in our numbers. Okay, good. So Kc is 50. My bromine chloride at equilibrium is 2x. You got to put that up there. Just don't forget to what? Square it, because it's the concentration of bromine chloride squared. Right? That guy is squared. Chlorine. What do you put in for the concentration of chlorine at equilibrium? 3 minus x. Chlorine is 5 minus x. Okay. Yeah. Now we're stuck with that quadratic. Genevieve, remember the goal of this quadratic thing is to get ax squared plus bx plus c equals 0. Get it in that format. You got a ways to go. What would you like to do first? Okay. Do that squared part. We'll have 50 equals, what's 2x quantity squared? 4x squared. Okay. What would you like to do next? Mallory? Oh, she wants to do the FOIL thing. Okay. So we'll have 50 equals 4x. You got to help me, Mallory, since I don't do FOIL.
I did it. That's squared minus 8x.
So multiply through by the 3?
Yeah.
And you're going to have 15. And then you multiply through by the negative x, and you're going to have negative 5x plus x squared. Okay? Okay? Adrian, what do you want to do now?
Now you find like terms.
Okay. That's a good idea. If there are any, and there are, what do you end up with?
X squared plus minus 8x plus.
Okay. See what he combined? The negative 3x and negative 5x. We're getting there, Lewis. Now what? Okay, that diagonal thing. You got to get the 50, 15 minus 8x. Now that whole thing is supposed to equal what? If you followed the diagonal. Right now it equals 4x squared. Right. Okay. Whoop, ran out of space. So Javier, remember the goal. AX squared plus BX plus C equals 0. What would you like to do now? Yeah, I think that's a good idea. Let's multiply that 50 through. 50 times 15 is like 750. And then 50 times a negative 8 is a negative 400. And 50 times x squared is 50x squared. That whole thing has to be 4x squared. Okay. Matteo.
Now you want to make it equal to 0?
Yeah. Okay.
Easiest thing to subtract 4x squared.
Let's subtract 4x squared from both sides. You end up with what in front of the x squared? 46. Let's write him first because that's my a. Minus 400x plus 750. Okay. Now I know what my a, b, and my c are. Right? My a is 46. B is negative 400. That's a big deal. And my c is 750. Now I gave you the quadratic equation, but it's probably going to be burned in your head pretty soon. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah. Okay. So, different color here. Negative b, that's going to be positive 400 plus or minus. Negative 400 squared minus 4. A was 46. C was 750. All over 2 times 46. Now what you could have done, you could have divided all through by that equation. This one right here, you could have divided them all by 46 if you want. And then you have smaller numbers everywhere. But I say you have a calculator, so why mess with it? Just keep going, right? Less steps. Okay. Okay. Hopefully.
You want decimal?
Hopefully, 3-4 digits, let's carry 3-4 digits all the way through. 400 plus or minus 148 over 92. So, you end up with something or x equals something. So, 400 plus 148. Divide that by 92. About around 6, 5.96 or so. 400 minus 148 divided by 92. I get about 2.74. Okay. Makes sense. Okay. Okay. Well, what's a negative number squared? Negative goes away. Remember, it's negative b. Amanda, look, negative b. So you have to put a minus in front of the negative 400. It ends up being positive 400. Okay, we have two possibilities. And remember, we want to write out, let's write out our answers here, our equilibrium composition. Chlorine was 3 minus x. Chlorine is 3 minus x. Whoop. And what else were our answers? We had bromine is 5 minus x. And we had one more. BRCl, thanks. BRCl 2x. That's the thing, yeah. If we have two X's, we can't have two concentrations. I mean, it seems like everybody got the 5.96 and the 2.74. I think those numbers are right. You can't have two concentrations.
No. What if this bond from?
Okay. You have 3 minus X and 5 minus X. The 2X you really can't go by. Can you have a negative concentration? No. So only one answer is going to make sense. The 2.74. That's what you kind of got to look at. Only one of these makes sense. So that's going to be minus 2.74. 5 minus 2.74. 2 times 2.74. Because the 5.96 is too big. You get negative answers with it. Okay, so what do you get? 0.26. Thank you, sir. What's that one? 5.28? 5.48. Thank you, sir. Okay, you go through all that work, get all those answers, and Smith still takes. You don't have the big M. You got to have units on your answers. You could write moles over liters, but big M's faster. Okay? It's horrible. All right.
You don't put like moles of CO2.
Well, it's kind of, you should, but it's the way this is written, Jessica, if you go all the way across,
Okay, but
it's all there.
so if we do
But
it differently, then
if you do it differently, you should write this. You should write that. Okay. But if your work isn't clear, linear, yeah, that's a good point. Linear isn't right. Okay. So this is a different type of question than what we had. It's not asking, hey, are we at equilibrium or not? That's QC problem. This is equilibrium, not equilibrium composition. Equilibrium composition. Burn that in, man. And that means you got to list every single reactant, every single product, and list their concentration. Like that, in the box. Okay. But extra spaces, Adrian, like this question can really throw you off. Look at all the space you've got on this question. And it says, solely on the basis of the value of Kc, would this reaction go to near completion at equilibrium? Now, what does near completion mean, Vanessa? What does near completion mean? I know, to me it's a poor choice of words. We just have to get used to it. A dude who uses this type of terminology is a guy who's synthesizing this drug that is worth a lot of money. He wants this reaction to go to full completion. So do the people hiring him. What does that mean? What that means is that once you reach equilibrium, you hardly have anything left. Any reactant. It almost all got converted to product. Now, all equilibria aren't like that at all. Some, you just barely get going and they're out of oomph, right? They form very little product, a lot of reactants. So these Kc, these numerical equilibrium values, they're all over the place. Does this reaction go to completion using their terminology, their words? What is that K? What would you expect for K? Yeah, this K is really, really small. What was K again? That's really, really small. K is what over what? Product over reactant. If you want a reaction to go to completion, you want a lot of product. So K is going to be huge. This K is small, super small. So that's not even close, right? No way is that going to go to completion. Kc is extremely small, 10 to the negative 31. Yeah. Okay, so Remember how, Adrian, you mentioned, hey, will you give us a lot of paper? Yeah, but that can go both ways. Conceptual question. There's nothing to calculate. Okay? Does that make sense? No, that's okay. Sylvia, we've got some choice problems. We've got, is the reaction go to completion? Is the reaction quotient problem, the QC problem? Or we've got the one where we have to list out all the concentrations of everything and draw a box around it. Which type of problem is this one? Look for two words. Equilibrium, composition. Then it's the really long one. You don't want to see those two words in a homework question because it's going to be a lot of work, right? But burn it in. That's what it is. It guides you. What's the equilibrium composition? So you at equilibrium, the concentration of every single reactant and product, and then draw a box on it. Ray, where would you start? With the ice. Yeah. PCl3. Make the columns first. Whoa. Plus chlorine. That goes to PCl5. And you said do the ice. So on the initial row, Nick, under the phosphorus trichloride, what would you put? Oh, he's calculating it, right? He's dividing the PCl3. You're dividing what by what, Nick? Yeah, the 0.4 by the 4, and you get, right, 0.1? Yeah, it's 0.4. So 0.4 over 4, 0.1. So that should be 0.1. The chlorine, everybody should be, yeah, so they have the same number of moles. The phosphorus pentachloride, a dash. Change row. Victoria. Negative X. For both of them, yeah. Yeah. Right? She's using the stoichiometric coefficient. Our answer is destiny, the equilibrium row. 1 minus X and X. All right, so remember where our answers are it. Those are our answers. So Eddie. Answers involve X, so that's not going to cut it. What do we do next? Right, the Kc expression. Right. Kc L5 all over A and Cl2. Okay. So again, I strongly recommend writing that Kc expression. There's no place to really screw up this time, but otherwise it's too much math, too much work to make such a silly mistake. Okay, so we're going to have X. Oh, I forgot my Kc. That was what, 49? Okay. And you got to work it out. See what you can get for X. I'll be glad to help you. Just ask. Yeah, always negative, because all you have initially are the reactants. So these numbers have to go down. This number has to get bigger because there's nothing there. Yeah, always be minus for reactants, positive for products. In fact, that's probably where that QC thing comes in. If you did the QC thing, you'd find out that QC is way too small. Okay, I stole this off of somebody. Did anybody else get the same numbers for A, B, and C? 49, negative 10.8, and 0.49? Yes. Okay. Get those. If you got those, you're on the right track. Now, if you have a negative 49 for your A, that's fine. But then all these guys, 10.8, negative 0.49. If you have a 1 for your A, just divide the B and the C by 49 also. They'll all work. Oh, those are your. So. Okay. Okay, we just added wrong here. So yeah. Negative 0.1, negative 0.1, negative 0.2x. Okay. Then you bring it up here, you multiply negative 0.2 times 49. Yeah, I got 9. Okay, and then you got to bring the negative x over. That's equals 0. So negative 9.8 and negative x would be negative 10.8. The whole thing has to equal 0.
Oh, okay.
You got it. You got it. As long as you're carrying 3-4 digits, you'll be good. Yeah, you just forgot to bring this guy over.
Oh.
It equals x.
Oh.
So you have to add a negative x to both sides, wherever your work is. You got a negative x to both sides. Okay. So negative 9.8 and a negative x would be negative 10.8. Okay. Anybody get some x's yet? What do you get for your x? 0.06 and... Okay, did anybody else get that? Okay. Several people got that, so I bet you those are the x's. So no matter what you have for your A, B, and C, those are your x's. One of them won't make sense.
The other one, the one that G equals 0.6.
Yeah, exactly. 0.16 is way too big.
No way to say.
Bless you.
Oh, thank you.
Really? PCL2.
Yeah, we did. So I got 0.036 for both of the CL3 and CO2.
Yeah, it'll be pretty dang close. And don't forget to put big M's on there.
Oh yeah, we got it up.
Yeah, we're done.
Okay.
No, I got that short. Like.
So come by if you have some questions. I'll be glad to help you out on this stuff. Lab this week, 8:30. All right, Tuesday and Thursday. 26.